Okay, so in this video, I want to go through how we can analyze multi-loop circuits. So here's the goal. The goal is to work through this circuit, and we want to find the currents through each resistor. And then once we find the currents through each resistor, we want to find the voltage drop across each resistor. And then we will use that to deduce the power that must be absorbed by each resistor. Or actually, would be, what really happens is the battery gives the electricity or the charges energy. As they pass through the resistors, they basically give that energy into the body of the resistor. And then since it runs in steady state, it radiates that away in the form of heat. But okay, so what we really are going to try to do is find the power which must be delivered by this battery. I should have given you a number. I'll say it's 3 volts. So I want to know, what is the power delivered by this battery to the circuit? So we're going to do this in 2 ways. The first way is we're going to use parallel and series resistors to kind of work it all out to get numbers. And then we're going to use Kirchhoff's laws to get the same answer. When we get to Kirchhoff's laws, I'm just going to show that we get the same currents, and once you have that, the rest is just arithmetic. Okay, so let's use equivalent resistors. So when using the method of equivalent resistors, you can, because this part of the circuit only has resistors, there's not another battery, and there's nothing like some other wire that splits off and goes to some unknown component. We don't have any problem with that. So I can use equivalent resistors to, I would use the parallel rule to smush these together to get an equivalent number, quantity. And then once I have that, I can smush these together to get one overall big resistor. Once I know that, I can determine the current through the overall pair of, or set of resistors, and then I can work things out from there. So that's what I'm going to do. So the first thing to do is to combine these into one combined resistor. So that would be 1 over 2 plus 1 over 3 gives me 5/6. So therefore, this thing could be replaced with a resistor which had size 6/5 ohms. And then I can combine that with the 1 ohm resistor to say that I have overall a 3 volt battery combined with a 1 plus 6/5, that's an 11/5 ohm resistor after I smush it all together. And I have current I1, which is the overall current that flows into the entire system of resistors. And so I can immediately determine that I1 equals, so V equals IR, here's R, so I1 is 3 divided by 11/5, that's going to be 3 times 5 over 11 equals 15/11. 1.36 amps. Okay? So I can think of this circuit as one giant block with this equivalent resistance, and I compute an amps, 1.36 amps. So that's the current. The voltage drop across this entire set of resistors would be, well, I'd say V equals IR. So that was the current. The voltage drop total is equal to IR. So to get that, I would just say the voltage drop equals the current times 11 divided by 5. Which is 3. Duh. Because it's in parallel with a 3-volt battery. Yeah. So the voltage drop is 3. I shouldn't have had to do that. Sorry. Okay, so the voltage drop is 3. I guess it just shows that I can type things in right. Okay, now the formula for the power, which must be delivered by the battery, is P equals I times V. So the current is 1.36. V is 3 volts. And that gives me a power of 4.08 watts. Because the unit of power is watts in the metric system. Okay, so that's the power that must be delivered by this battery, or this power supply. Must be a 4-watt power supply, or else it'll burn out. Okay. What remains to be done is to find the voltage drop across, or sorry, the current through each of the separate resistors. Okay, so I'm going to write my numbers here just so I remember them. So I1 equaled 1.36. So now let's work out the resistance, the voltage drop across, or the current through each of the other resistors. To work out the voltage drop across R1, I would say voltage 1 equals I1, which I know, times the resistance 1, which is 1 ohm. So that's going to be 1.36. So we know that the voltage drop across this resistor, is 1.36 volts. On the other hand, if you think about it, you gain 3 volts here, you lose 1.36 here, but when you get all the way around, you're supposed to be back to 0 change. That means that the voltage drop across each of these must be 3 minus 1.36. So V2 must equal V3 equals 3 minus 1.36. So I do 3 minus 1.36, and that equals 1.64 volts. Okay, so you can look at this resistor or this resistor, it doesn't matter because they have the same voltage drop because they're in parallel. And what I see is that basically the total voltage that was gained going across the battery is 3 volts. All of that must be lost by the time the current gets back to here. Some of it gets lost in the first resistor, the rest must be lost across the parallel resistors. Okay, but now if I know the voltage drop across resistor 2, I would say that the voltage drop across 2 equals the current through 2 times the resistance through at 2, which is just 2 ohms, So that tells me the current through resistor 2 is equal to 1.64 divided by 2. So that's going to be 0.82 amps. So I have the current through resistor 1 is 1.36. The current through resistor 2 is 0.82 amps. And then I can use current charge conservation or the current rule to say that the sum of the currents in equals the sum of the currents out, to say that I3 must equal the difference between these. So 1.36 minus 0.82, and that means 0.54 amps. Does that make sense? Well, let's see. What you'll notice is that the larger resistor received a smaller current, and the smaller resistor received a larger current. What you notice is that the ratios of the currents are inverted, or the inverse ratio of the resistors. So I2 divided by I3 equals R3 divided by R2. Now, there are various rules of thumb. People will talk about, say, the electricity follows the path of least resistance, things like that. That's not really true. It's like a water flow. It goes through every possible path, but the amount which follows each particular path is adjusted such that the more resistive paths have less current flow and the least resistive paths have more current flow. So when you say that it follows the path of least resistance, that's really only true if one of the paths essentially has no resistance. Then I guess you could imagine all of it goes through there. But in real systems, every possible path carries a little bit of current. The real issue is just how much current does it carry. Okay, so this is how I went through this analysis using parallel and series circuits, and I basically solved for every possible number you could want. I found the voltage drop across each resistor. I found the power radiated through the whole circuit. If you wanted to, you could work backwards and get the power radiated through each individual resistor. And then I found the current through each resistor. I'm going to work to get these same numbers using just Kirchhoff's laws, not using parallel and series resistors, and just to show you that you get the same answer. Kirchhoff's laws are guaranteed to always work for any set of devices, not just resistors. You can mix resistors and capacitors and inductors, and you can get them, you can write down Kirchhoff's laws for that situation, and it all works out, always. So it's kind of like the safety method. All right, so I have a battery here which was 3 volts. And I had a 1 ohm resistor here. I had a 2 ohm resistor here, and I had a 3 ohm resistor here. And I have I1, I2, I3. So I have 3 unknown currents. So for me to solve for them, I need to come up with 3 equations. Kirchhoff gave me 2 rules. He gave me the loop rule, and he gave me the current rule. So how many loops do I have? I have a loop here, I have a loop here, and then I have a big loop. It turns out algebraically, The equation you get for the big loop is just a linear combination of the two smaller ones. So there are only two separate or two independent loop equations. The other equation I have is a junction rule, which says that the current into this joint is equal to the sum of the currents leaving the joint. So let's just grind through it. This loop rule here says that I'm going to start here and walk around. I'm going to get 3 volts. I'm going with current I1, so I get minus I1 times 1 ohms. Minus, now on this branch, the current is I2 times 2 ohms. And then I get back to where I started. I have another loop over here, which tells me that, so okay, I'm going to start here, and I'm going to follow it like that. I'm going to follow it clockwise. But if I follow it clockwise, when I cross this resistor, I'm actually going in the direction of opposite the current flow. So that actually looks like a gain of energy. So it's plus I2 times 2. Now I'm going with the current minus I3 times 3 equals 0, because I'm back to where I started. And then the last equation says that I1 equals I2 plus I3. Okay, so now I have to solve these equations. You could use your calculator. If matrices would do this stuff pretty fast. I don't have one right here, so I'll just do it kind of on the fly. So, well, let me make this not look so negative. So I'm going to get 3 volts. 3 equals I1 plus 2I2. And I'm going to have, this one says that 2I2 equals 3I1. And then I have this, which says I1 equals I2 plus I3. Sorry, this should have been 3I3. Well, if I take this equation and use these two, I immediately find that I can write this and say I1 is I2 plus 3 halves, no, plus 2/3 I2. So I get I2 plus 2/3 I2, which is the same as 5/3 I2. That's what I1 is 5/3 I2. And then I can substitute that into here, and I'm going to get 5/3 I2 plus 2I2. That's going to be 6/3 plus 5/3 is going to be 11/3 I2 equals 3 volts. So I2 is going to be 9 divided by 11. Oh, shoot. I fouled up my stuff. Do that again. I apologize. I hope I didn't make a mistake in my other calculation. Working through the little details. Should an I2 Hold on a second. Oh, no. I'm sorry. It's the same. I'm sorry. It's just a rounding issue. I apologize. It's now 1 in the morning, so I'm a little loopy here. I just was misremembering the result. So okay, so I'm just doing the algebra from the rules. I plug it in here, and I get that 3 volts equals 11 thirds I2. And what you get from that is that I2 is 0.82818 actually amps. I think last time I must have rounded. I think I had 0.82 last time. Looks like in my calculator. Okay. And then I can multiply that by 2/3 to get I3. And that says that I3, coming from this equation, equals 0.545 amps. And from this equation, I can add them and I get the same answer. So I get I1 is 1.36 amps. So using Kirchhoff's loop and junction rule, I get to the same place that I had when using parallel and series resistors. You know, Kirchhoff's laws are always going to work, always. Sometimes the actual arithmetic is a little simpler if you use parallel and series resistor formulas. That being said, those don't work if you have more complicated circuits with other kinds of devices. It's not so clear what to do. Just a comment. I talked about Kirchhoff's laws and I identified a loop, but you notice I did not ever talk about the loop current. So for those of you who took linear electrical circuits, one of the ways you learn to analyze currents or loops is to say, circuits, is to say that each loop had a separate quote unquote loop current that went around, and you thought of it as like a current associated with this loop alone and a current associated with this loop alone. But then the physical current, the real current, if you were standing right here, the actual current you get would be kind of the downward flow from one loop and the upward flow from the other loop, and you'd have to add them in some way to combine them to get the physical current. That's a fine, again, these are linear equations, and really you're just playing games with matrices, taking rows and columns and taking linear combinations of things. That's probably a very efficient way to solve complicated systems. But because in this class I want my currents to be real currents, because I want to kind of stay anchored to the physical quantity. So when I talk about the current on this branch, I mean the physical current that passes through that resistor. So I won't ever talk about a loop current, which is sort of a fake thing. It's just an intermediate step for doing algebra, not really a physical thing. Okay, so that's just a little comment for those of you who took linear electrical circuits. Okay, sorry for the little confusion. I'm getting a little fatigued.